All right, so last time we left off at exercise 8.1. So the idea is that we're going to, instead of thinking of x and y's as being random here for this part 1, we're going to think of just t as being, the index as being drawn uniformly at random from 1 to n. So now the question is, when we just think of that t as random, so we're taking the expectation only with respect to t, where this expectation is taken only with respect to the random draw of t, what is this expectation, right? So before we had that x and y, those were thought of as random, and we had that the expectation of this was the gradient of the true risk. But now we're just thinking of the index as random. Okay, so let's answer that first. Okay, so the first thing, that expectation with respect to the random draw, t, this is just the gradient here, and this is equal to 1 over n times the sum, t equals 1 to n, of this gradient of the loss at xi and yi. So this should be xt, yt. This should be expectation with respect to t. And so this average is just the gradient of the empirical risk. I'll make those corrections really quickly. Okay, so I just made these notational corrections. So the expectation with respect to the draw of t, that's the average over the samples of the gradient of this loss. This turns out to be the gradient of the empirical risk. And this is also an important distinction. So if we didn't draw the t's uniformly at random, say we had a biased random sample, so like maybe we served up, we didn't shuffle our data points when we started to reveal them to the learner, then they might not have been drawn IID. They might have been ordered based on one of the covariates, and then this wouldn't have been a random draw. And so we wouldn't have the fact that if we just did random draws, we get the gradient of the empirical risk back out. Instead, if we didn't do that shuffling, we would get something that's biased. It's no longer a good estimate or an unbiased estimate of this gradient of this true risk or the empirical risk. And this gradient of the empirical risk, this is what we would use in batch gradient descent. And so with stochastic gradient descent, this isn't, we are going to just use one or a few of these. Okay, so the question 2. Yeah. Okay, question 2. So for the previous cell, we have beta and beta naught are fixed, so just suppose that they're fixed. Now also suppose that yi actually does follow a linear model, which says that it's equal to some intercept term, beta naught star, plus xi transpose beta star, where beta star is an RD, plus some epsilon I, and critically that epsilon I is zero mean and independent of the xi. We call this exogenous noise, and we'll use this assumption throughout. So what is the expected gradients in the previous cell? So the previous cell, we had this, one of the gradient steps was the delta I, that's for the intercept, and then delta I times xi, that's for the remainder of beta. So let's think about what these expectations are. Now we're thinking of x and y as random in this case. So first of all, let's plug in our y-hats. Our y-hats are beta naught plus beta transpose xi. So let's just focus on the delta I term first. So this is the intercept term. Its expectation, let's just plug in what delta I means. This is 2 times the y-hat minus y, so the expectation of y-hat minus y. But y-hat takes this linear form. Actually, y also takes a linear form plus some epsilon I. And that linear form also, it's the same thing as this, except it's beta naught star and beta hat star, or beta star. And so we get the beta minus beta star here, and the beta naught minus beta naught star here. We have the expectation of xi appearing. And then the epsilon I, what happened to the epsilon I? Well, it has expectation 0. And so it goes away. And so this is what our expected gradient step is for this case. So the expectation of xi, that's the expectation of x, they're drawn IID. So, you know, if we thought of them as, say, having 0 mean as well, then this would be 0, and we'd only be updating the intercept, which would make sense. So you could think of your xi's as being centered by their true mean. subtract off their true mean or a good estimate of it, and then this is 0. This expectation of xi is 0, and then we'd only be updating based on the with expectation based on the intercept. So let's look at the delta I times xi term. We have 2 times beta naught plus beta transpose xi minus yi. That's the same delta I term here, and then just multiply by xi. There should be an, yeah, so that's that. This is correct, actually. So this is equal to 2 times beta naught minus beta star plus beta transpose xi minus beta star transpose xi minus epsilon I, right? So the epsilon I comes out of the yi here, and then you have this term, right? And then you end up multiplying it by xi. So you have all of this, right? And this is just expanding out what everything means using the, so this should be, yeah, using the definition of yi, right? And so if we just take the expectation of this thing, well, we get the expectations of xi's, but they're multiplied by xi as well. And so you end up getting xi transpose wherever we need it. That's what ends up happening. So we'll see that here. You have the epsilon I term. You have an expectation of epsilon I times xi. But like I said, they're endogenous. So these are independent. This has 0 means, and so this expectation is actually 0. Right? And so you end up having just this term here, and it gets expanded out there by exogeneity. That's what you get. Okay, so what does this tell us? You know, how can we interpret this? Well, let's suppose that our intercept term is this intercept term should be multiplied by the expectation of xi. So I'll correct that right away as well. Okay, corrected that. So you have this beta minus beta star times this expectation of xi transpose. You have this beta naught minus beta naught star. So this is just based on the intercept terms times expectation of xi. So let's just think about what happens if xi has mean 0 as well. And so there's some intercept term, and then there's centered x's in expectation. Then you have that this term would go to 0. You're only updating based on the intercept. Here, this term would go to 0. And so the update based on beta is based on this. This term, when xi has mean 0, is just the true covariance matrix for the x's. And so this is like the covariance matrix times beta minus beta star, which is sort of interesting to think about. Okay, so we're going to evaluate these methods on the Wine data set, our favorite data set, just for unit testing purposes. So we're going to center and normalize the X matrix and pull out the Y's. Okay, so I have created a module which you have access to on this repository. You can either look at it now or afterwards. This decay term is going to determine how that eta changes over time. So the eta is that learning rate. Here, let's jump back. Here's the eta. So I'm actually going to make it change as we see more samples. This is called a learning schedule. We'll talk more about learning schedules in the future. So that's what this decay rate does. And when I specify this loss to be the square loss, that's just using the previous example, using exactly the form that I had before. And so, you know, one thing is that's a pretty nice example of a module. I would encourage you to look at it. One thing is there are doc strings in the module, so I can always look at the help for my methods. For example, the method update beta. It has a single step. It says it's a single step update. So it's an update for stochastic gradient descent. It outputs the loss, and the arguments are the x and y. It's the x vector and the y scalar. So not a detailed doc string, but it's something. Let's just look at what happens if we pull one of these xy pairs. So I'm going to write a for loop with all the x's and y's, but thinking of as if we're doing the Wine using the wine data set in an online learning setting. So we're just going to for loop through the whole wine data set, spitting out a y-x pair in sequence. So then if we look at the learner beta, the initial beta, it's all zeros, so it initializes at all zeros. The y for this first sample is 5, and the x for the first sample is this. Okay. And then if we apply this update beta, what it does is it takes the x and y, it will update, first of all, it'll make your prediction. Then it will update your beta, and then it will compute and return your loss. So it does everything in the online learning step. It will make a prediction, see what the loss was for that prediction, and it'll update your beta based on the gradient descent method that we just went over. Okay, so learner.beta, if we look at the new beta, it's this, right? And this actually shouldn't be too strange. So it starts off as it started off as 0. So now it's minus 211.27. So this should look familiar. It's 10 times this first x coordinate, right? And this is 10 times the second x coordinate. So we're just moving in the direction of the x coordinate. 10, why 10? Well, remember that eta is based off of y hat minus y, and we were predicting with all zeros. We just predicted 0, right? And so 0 was the prediction, and then we were updating the initial prediction. Y was actually 5, and then we multiplied by 2, right? So we had 2 times 5 times x, or 2 times 5 times the intercept. And so this is the new beta, if we look at the new beta. And so this isn't a surprising update, but these are huge numbers, right? And so if we just apply this to all of our data, so try to figure out what this is doing. Remember, this is an iterator, or just made from the zip command. We had already applied next to it, so it's going to just start with a second data point and move on. We're going to just update the beta as we go along. So this is going to update the beta, and each time it does this, it outputs a loss. And so we're going to wrap up all those losses in a list comprehension, and then we're just going to see what those losses look like. So this is applying the online learning setting with our algorithm. Oh, it looks like the losses diverge. And that isn't too surprising. If you look at this, this warning makes us think that the losses are diverging. So the losses diverge. So first lesson, there is no guarantee that when you apply a gradient descent method or a stochastic gradient descent method to your data set, there's no guarantee that it's going to work. You don't know the details of your loss surface for your data set in particular. The appropriate learning schedule is going to change with the loss function that you're using. It's going to change with the learner that you're using, so like linear learner in this case. And so there's no reason to think that your specific gradient descent method is going to work in this case. And there's no reason to think that your loss is well aligned with this data set in the sense that it's going to give you good convergence properties. And so it turns out to actually diverge in this case. So one modification that I'm going to do is I'm going to use the absolute value instead of the square. So let's think about this loss. So this is just the absolute deviation loss. A subgradient of this is just the sign of this difference, right? That's what, if we use the chain rule, it'd just be the sign of this difference times our xi and then the sign of this difference here. Now we could just call the sign of this difference delta I, and delta I again is a scalar, but now it's the sign of yi hat minus yi. In the case that yi hat is equal to yi, we're just going to say that the sign is equal to 0. That's a common convention. So if we make this update, we have beta is updated with beta minus eta. This is our learning rate, times delta I times xi. Okay? So this is our gradient descent update here. Our beta naught update, our intercept update, is going to be beta naught gets beta naught minus eta times delta I. So it's exactly the same update as before. It's just that delta I, instead of being a number that can be very large, we saw it started off as 10 and just blew up, it seemed like. It's actually controlled. It's a number that's bounded between -1 and 1. Okay, so let's do this. I actually have a separate loss or argument. Loss can take the absolute value loss now. I have a closed form gradient calculation in the in this LR online module. So the losses, these are equal to learner.update beta x and y for x, y in this zip. So we're just going to apply this again to our data set. We're zipping up our data just like before, and we're just going to apply this new method. And it looks like the losses converge and approach 0, actually. So this, for some reason, stochastic gradient descent with this absolute deviation loss, absolute error loss, is actually working quite well. And there was nothing that told me that this is what was going to happen. It was just something that I had experimented with in some sense. And I had some intuition that I needed to control the gradients, because I saw that the gradients were very large at the beginning of the square error loss version, but then, you know, because they were unbounded, they were uncontrolled in any sense, they blew up. Whereas here, I knew that the gradient is controlled because the stochastic gradient descent method works that way. Okay, so as an exercise, I would like you to look at the module and determine what that decay argument is doing. So just look at that module. It's a pretty good example of a way to write a short, sweet module. And then try to play with the arguments and see when you achieve convergence and when you do not.